to everyone. Um, I am Joshua, one of the co-conveners of the Cambridge Disaster Research Network. Today, we are very excited to have Professor Scott McDougall from the University of British Columbia joining us. Professor McDougall is the director of the Geological Engineering Program at UBC, the University of British Columbia. He is a civil engineer by trade, originally a civil engineer. He maintains his professional engineering designation, but his work and interest and practice has moved more towards geological and geotechnical engineering over the course of his career. He's worked in industry, and for the almost a decade, if I'm correct, he's been at UBC after his time in industry has been teaching at UBC. Scott's main focus of work is in mass movements and geomorphology broadly speaking, and looking at hazards and ways that we can reduce risks. So we're very excited to have him here today. I think, again, it was an exciting opportunity to have someone from industry and from academia sort of talking about a more applied aspect of disasters than some of the conversations that we sometimes have, because all are worthwhile to engage in. So I'll allow Scott to introduce his presentation and give his presentation, and then at the end there'll be time for some questions and answers with Scott. So yes, thank you very much. I'll stop rambling and pass over to you, Scott.
Yeah, thanks, Joshua, and thanks for the invitation to join this group. It's early in the morning here in Western Canada, where I'm calling from. So apologies. I have had some issues with my coffee maker the last few days, and even with coffee, I usually just communicate through grunts until about 9 a.m. It's 7 a.m. here now, so we'll see how this goes today. But thanks for joining me. And yeah, special thanks to Joshua for the invitation. Joshua went through the geological engineering program here at UBC many years ago now, I guess, and was one of the best students to come out of our program in the time that I've been there. And so it's always great to catch up with Joshua, and I've been following his work and interested to learn more about the Disaster Research Network there at Cambridge as well. So Joshua introduced me nicely, so thanks for that. I'm actually here kind of representing a pretty large team of combination of academic partners and industry partners, and you can kind of see all the logos on the screen there. Joshua mentioned that you were specifically interested in waste-related disasters this year, and so I've been involved in this research project related to mine waste for the last several years, I think going back to 2019 or even slightly before that, with this large group of industry partners and academic partners. So I'll describe that a little bit as we go. And as Joshua mentioned, I came from a consulting background before coming back to academia to do research. And so a lot of the research questions that we're addressing in this project are related to questions that our consulting partners have, and even questions that I had going back 20 to 25 years ago when I started my own practice. So the goal of this talk today is to try to give an overview of recent and ongoing research related specifically to mine waste failures. I've kind of split things into three different sections of the talk. I want to give kind of an overview of the motivation behind this project and our main goals, and describe the structure of the research project as well, because I think that's kind of interesting. I'm going to summarize some of the key outcomes to date. So this is a project that's been ongoing for 5 or 6 years now. It's kind of split into two parts. We had a sort of 4-year main push up until a couple years ago, where we had a bunch of graduate students working and getting through, focused on the research, and then applied for another round of funding to extend the project for another 4 years. So that just kicked in now. So I'm going to also talk about some of the ongoing work that we're doing and the future work as we're bringing new graduate students in to join the project over the next year or two. And I should say I'm getting flashbacks to online teaching here. I haven't done this kind of thing for a couple of years, but I see everyone's, got their cameras turned off and you're listening with your microphones off. But feel free to turn your mics on and interrupt me at any time if you have any questions as I go. I'm not sure what the tradition is in this group to hold questions till the end, but yeah, like I said, rambling myself at 7 o'clock in the morning is a challenge. So I welcome any interruptions along the way. So yeah, just talking about the project overall and some of the motivation behind it. And I wasn't sure everyone's background here, so I thought I'd give kind of a little primer on just mine waste in general. A couple definitions. So ore is the rock that contains minerals that we're extracting to make resources and ultimately money. And there's two main kinds of mine waste, at least on the geotechnical side of things. So one is waste rock, and I'll talk a little bit more about waste rock towards the end of the talk here. It's the rock that's removed to get to the ore. So it's typically coarse-grained material, relatively coarse-grained sand to boulder-sized grains, and you can see the way that it's stored here, basically dumped out of large haul trucks into these steep piles. It can contain contaminants. It can generate acid when in contact with water and oxygen, and so it is a hazardous, potentially hazardous material, not just geotechnically. The main type of mine waste that I'm going to talk about through this talk is called tailings, and it's the material that's actually left over after extracting the minerals from the ore. So it's all the ground up material that's gone through the mill. It's been crushed, it's been ground, and then the minerals, valuable minerals have been extracted. And so you're left with this relatively fine grained material, clay to sand sized grains that are typically wet. They may also be acid generating like waste rock, and they may contain other contaminants, including chemicals that might be used to extract the minerals through the process. So potentially hazardous material again. And they're stored a little bit differently, although there are some parallels with the waste rock storage. They're typically transported as a slurry, so like a saturated fine-grained material through pipelines to a storage facility where they're deposited behind dams. And so you can see an example in the photo here of a large tailings storage facility. And one of the unique things about these types of dams that are, separate them from water retaining dams is that they're raised as the tailings deposits grow in height and lateral extent. So these structures are constructed as the waste material is being deposited in the impoundment, and the dams are raised concurrently. And so that creates some inherent stability challenges. A lot of it's related to the typical high water content of the material. So you do get saturated material stored behind these structures, and then separation of the water and often formation of a pond on top of the storage facility. The other kind of unique thing is just the nature of the long timelines of constructing these things. So unlike a water retaining dam that might be built in 1 year, a couple of years before it's actually filled up with water, these are raised over a number of years, even decades. And so there's issues also with continuity of the workforce that's involved in the construction, and just knowledge of the history as these things are being raised. So that's a huge challenge with construction of these facilities as well. And there's different ways of raising them. You can see on the right-hand side here, either raising them upstream on top of the tailings materials that are deposited in the impoundment, and that's a relatively unstable way of storing tailings. Another method is to construct the dam downstream as things are raised in behind, and then there's sort of a hybrid approach of the centerline construction that's shown in the bottom figure. And these things are potentially huge. Some tailing storage facilities are among the largest human-made structures on Earth. You can clearly see them in satellite images, and this is just an example of a large tailings pond in the oil sands area of Western Canada, and it's several kilometers across. You can maybe see some of the heavy equipment, tiny little specks on the landscape here. And so there's millions of cubic meters of water and fine grained material that's stored in behind here and potentially liquefiable. And if there is a breach, it would flow catastrophically. And these kinds of failures have happened historically. This is just one example that kind of hit close to home. About 10 years ago here in British Columbia in Western Canada, there was a breach of this facility. You can see this photo is looking upstream at the dam, the impoundment in the background, and you can see that the materials flowed through the breach, and huge proportion of the material that was stored there has now exited the impoundment. About 25 million cubic meters of material was released in this case. Um, the breach was caused by an unstable dam foundation. So the dam itself slid out on this foundation material and created conditions for overtopping and material in behind subsequently overtopped and breached and traveled up to 9 kilometers downstream. I'll show you in the next slide a photo of the impacts there. There were about, in terms of direct cleanup costs, about $67 million in Canadian dollars. And then, huge losses for the mine itself in terms of lost production, share values, and so on, and as well as, lawsuits that came out of this. This is a photo about 9 kilometers downstream of that breach, looking upstream. The impoundment would be off the photo to the far upper right here. And this is where the material flowed down this river into a large lake, and you can see some of the impacts at the lake here. In the foreground, they look like tiny little matchsticks, but those are trees that have been taken out by this swath of destruction as it came down this river here. And you can see sediment plume as well in the lake. And this happened 10 years ago, and the monitoring of contamination is still ongoing today. And like I said, this was hit close to home here in Western Canada, and it was a wake-up call for the Canadian mining and geotechnical communities here. It led to new legislation and new professional practice standards for tailings and engineers in Canada, including some specific requirements for site investigation of dam foundation and glacial environments that we find here in Western Canada. So a huge catalyst for change in the mining industry here. But these kinds of failures continue to happen around the world. And just a year after the Mount Polley failure in Brazil, there was another breach of a tailings storage facility. This one known as the Fundão failure at the Samarco mine. In this case, larger than the Mount Polley failure in terms of material that was released, about 32 million cubic meters. And you can see in the photo on the left there, the destruction downstream of the facility that was breached. Unfortunately, in this case, there were fatalities, 19 fatalities. And just as an example of how far the damage can extend in these kinds of failures, there was a sediment plume that was created in the Atlantic Ocean from this failure, and that's more than 650 kilometers away from the mine site. The lower right image is kind of a famous photo from this event showing a car on top of a destroyed house. And then a few years after that failure in Brazil, another catastrophic failure of a tailings storage facility happened in the same area of Brazil. In this case, about 10 million cubic meters released. And in this case, unfortunately, a lot more fatalities, 272 fatalities. And I'm going to show this video of the failure. I'm not sure how many people have seen this, but a little bit different. Not a overtopping style failure. This tailings storage facility was actually not being raised at the time of the failure. It was a closed facility, and you'll see the catastrophic liquefaction that takes place as this thing fails. So you could see the nature of that failure, catastrophic liquefaction, and then the flowing of the material, the saturated material as it went through the mine site there, and many of the fatalities were because workers were stationed immediately downstream. Obviously, this failure wasn't anticipated. This is a satellite image just showing the downstream impacts of that failure the video that I just showed. You can see the tailing storage facility shown as the source in the upper right of this image, and then the red outline kind of outlines the main impact area downstream of the facility, and you can see the failure went through a town, Brumadinho, just downstream, and then met up with a main river where the flow was diluted by the river flow, where the outline changes from red to blue. And this graphic just kind of puts the size of those failures in context with all the other tailings dam failures that have been documented, at least publicly, since around 1965. So those three failures really, significant in terms of historically the volume of material that has been released in these kinds of failures. And obviously this spike in occurrence and consequences was a major concern for the public and the mining industry. And an important thing to point out on this graphic is these are just publicly documented failures, and we expect that there are lots of undisclosed failures that have happened over this time frame as well. And so there are a number of global international standards and local regulations and guidelines related to trying to assess the impacts of these kinds of failures before they happen, in terms of trying to prepare for emergency response. And following those failures, I mean, this stuff was in the works by the mining industry for a while, but obviously those significant failures were a catalyst for major change. And so a number of industry leaders in the mining industry got together and created this, what's shown in the middle of the screen here, this global industry standard on tailings management, which is kind of guidelines for the industry as a whole in terms of best practices for managing the risk associated with these mine waste storage facilities. And then there's also local regulations here in Canada. We have dam safety guidelines that tell us how we need to manage these things in terms of emergency preparedness, and then some specific guidelines for professional practice on actually how to carry out these kinds of analyses. But one of the main one of the main requirements in these guidelines, the global industry standard says one of the guiding principles in that standard is to prepare for emergency response to tailings facility failures. And so that means that we need to anticipate credible failures that may happen for these facilities and create inundation maps that can be used to communicate potential impact areas downstream and flow arrival times, things like flow deposit depths, so that emergency responders can prepare. And these maps are also used to classify dam failure consequences, which in turn, at least in the Canadian guidelines, determines the dam design criteria. So higher consequence dams have more stringent design criteria to minimize the potential for failure. And so a typical procedure for carrying out these tailings dam breach analyses, or TDBAs for short, is to split it into two main steps. And the first step is the breach analysis, where we look at the potential for material to leave the impoundment and how fast that might happen, the volume of material that may leave in the event of a breach. And then in step two, we take that information, basically generate this outflow hydrograph that shows the rate of potential flow out of the impoundment. And we run that through a numerical model or sometimes empirical methods that we can use to create inundation maps downstream, where we route the flow of material, given a certain volume and rate of inflow to the model and see what the potential impacts might be. And those maps are used to make decisions about emergency response. So one of the key challenges that we have, though, is that the methods that were developed for doing these kinds of dam breach analyses were originally developed for water retaining dams. And although there have been some adjustments over a number of years as practitioners have tried to adapt these for looking at tailings dam breaches, they haven't really up to this point been properly validated or calibrated for that kind of application. And so this has been recognized, and our industry partners and us got together to try to address this key challenge. And so the three big project goals that we've had over the last several years and going forward are to try to improve our understanding of tailings dam breach processes in general. How are they different from breaches of water retaining dams? How are they different from natural landslide and other mass movement processes? And then in the process of that research, try to actually develop better tailings dam breach analysis methods that can be used in practice by our partners and others. And along the way, this large group of this large partnership, one of our goals is also to try to foster a community of practice where practitioners who are involved in this research are exchanging ideas with each other, not necessarily competing with each other, but sharing information freely, sharing their best practices and trying to improve things overall as an industry. So the project is structured as this large collaborative research and development effort, sponsored with some sponsorship from the Canadian government, from the Natural Sciences and Engineering Research Council of Canada, and some matching funding from a collection of industry partners, including both operating mining companies and consulting engineers who do these kinds of tailings dam breach analyses. On the academic research side, it's been a collaboration between three universities. So myself at the University of British Columbia here in Western Canada, and our specialty is historically on the numerical modeling side of things. We've teamed up with Professor Steve Evans at the University of Waterloo, who's has a long history of doing great research on field and remote observations of mass movements. And then Andy Take is our other partner at Queen's University, and he's an expert on physical modeling. And Andy is also happens to be an alumnus of Cambridge University. He did his PhD there. And so we're trying to leverage the expertise at the three universities to try to pull together all those aspects of numerical modeling, physical modeling, and field and remote observations. And one of the unique facilities that we have at Queen's University is this long flume that's about 30 meters long and 2 meters wide, and it gives us some unique opportunities to run some experiments looking at dam breaches. So I mentioned that the project kind of goes back to 2019, and I want to kind of walk through, summarize some of the key outcomes to date, some of the things that we've learned, and the research that the graduate students have carried out since the start of the project. And I've kind of cherry picked main things, like sort of like summarizing six theses in under 10 minutes, I think. So it's a little bit of a challenge to pick out some of the key outcomes of the project. But one of the key things, we've created some new open access case history databases, and I'll describe that in a little bit more detail in a minute. We have explored some remote sensing opportunities to monitor these kinds of large facilities and try to understand the capabilities and limitations of that technology a little bit better. We've analyzed the case histories and come up with some new empirical relationships to try to estimate inundation areas from these kinds of catastrophic breaches. Just in a high level empirical way. And then we've looked in detail at numerical models, trying to benchmark different numerical models against each other, trying to better understand the sensitivities and uncertainties that are associated with that style of modeling. And then in the lab at Queen's University, we've done a number of experiments looking at tailing-specific dam geometry and also the influence of failure mechanisms on those breach outflow hydrographs, kind of a key input into the breach analyses that I'm describing. So as I go through some of these key contributions, you'll see some photos in the upper right. This is Nayan Rana, who finished his PhD a couple years ago at the University of Waterloo. And Nayan was leading things for us on the case study compilation side of things. And compilations like this did exist before, but they were sort of cobbled together from different sources, and it wasn't clear if, consistent definitions were being used for some of the observations that were made. So Nayan really went back to the source, trying to build the database from scratch using the best imagery available that he could find, and consistent definitions of things like runout distance. So in all of the case histories, we know that we're comparing apples to apples in terms of the measurements that Nayan did from the information that was available. Nayan also looked at the major causative factors associated with these historical failures, and develop some empirical relationships. An example shown here, just looking at the relationship between the impounded volume in these facilities and the outflow volume that's happened in some of these catastrophic breaches. He also did a really interesting job looking at just historical failure rates of these facilities and comparing them with water retaining dams, try to put that information in context to help with risk assessment. And Nayan's graduated now, but he's continued this work as a member of the International Commission on Large Dams. And he's compiled a database now of over 20,000 tailing storage facilities worldwide. So a huge piece of work that Nayan's contributed to over the last several years. He also took the opportunity, actually one of his original project goals was to get out in the field at some of these sites and do some actual field mapping, but unfortunately the pandemic got in the way of that, so he had to replace that with a investigation of remote sensing technologies. So Nayan was exploring the use of INSAR. This is satellite radar technology to monitor the movement of these facilities. And so there's a huge interest in industry for use of satellite INSAR for this kind of monitoring. And Nayan got information from a mine where they had monitoring data from measurements that were taken on the ground, and he was able to compare that with INSAR monitoring data and actually found really good correspondence. But in terms of trying to predict the failure of these events ahead of time, it's a real challenge with this kind of technology. At least at this time, the satellites that provide this information are only orbiting the same location every 7 days, and so to pick up on accelerations that might be happening in a shorter time period is just not possible with the technology as it is right now. There's some proprietary satellites and imagery that's coming online that may be useful for detecting some precursory accelerations before failure, but more work is needed to try to prove out that technology. On the University of British Columbia side of things, there was a PhD student here, Nagar Garamani, and she graduated a couple of years ago as well. And she was helping Nayan compile this database of case studies, and then diving into the measurements that were taken there. So, like I said, trying to use really consistent definitions for what's meant by impact area. So Nagar developed her own definitions of zone 1, the primary impact zone downstream, and you can see the image in the lower left there is the Fajal failure that I showed earlier. showing the outline of the zone one impact area downstream of the breach in red outline there. And she found a correlation between the volume of material that's released in these breaches. So looking at a number of case studies, um, and, uh, and and finding a correlation between the release volume and the area impacted downstream. And this is this sort of correlation has been found before for different types of mass movements, and you can see in the chart on the right-hand side of the screen there, the tailings flows that Nagar compiled are shown in the red dots, and other types of mass movements are shown in the various other colored dots on the screen. You can see they all kind of follow this same trend of increasing inundation area with increasing release volume. And then each subset of that data set follows a slightly different trend, mainly depending on the water content of the material. So tailings flows, they seem to fall somewhere between natural debris flows and natural volcanic debris flows that are a little bit more fluid. So it kind of helps us put these kinds of tailings dam breaches in context with other kinds of mass movements. And this information can also be used as like a screening level tool for estimating downstream impact area. And there was another student at UBC who actually wasn't working directly on our project, but working in the mining program here, who took this correlation and coded it into a simple GIS-based model that can actually, if you give it topographic information, the location of a dam, and release volume, it will actually automate the mapping of the impact area downstream. Nagar was also working in parallel with another graduate student here at UBC, Daniel Adria, and they were building this subset of case study data that could be used in numerical models. So sort of next level of detail that's needed to run a numerical model for these kinds of analyses. And so they were able to find enough information on 12 well-documented cases that they could set up numerical models and run some simulations to try to back analyze those failure cases. And so partly the goal was to benchmark different numerical models because a number of different models are used for this kind of thing in practice. And the capabilities and limitations of those models are not totally recognized. So we were trying to compare different model results, trying to understand collective opportunities for improvement in the models. And then another motive was to try to just build this database of detailed information where, other people around the world who might be using different numerical models could use this case study information to validate and calibrate their own models. So all that information is available in public open access databases now. Nagar was interested in trying to explore the sensitivity of numerical model results to some of the key input parameters. So she, along with Daniel, back analyzed a number of the cases that they were able to compile and adjusted the input parameters to look at how much the inundation areas, velocities, and so on downstream of these simulated breaches changed with changes in the input parameters. And so the sensitivity results are kind of summarized on the left there. You see a lot of the light colored blue shading, which shows us that the total release volume has a big impact on this the size of the zone one inundation area downstream of these breaches. So estimating the volume of a potential failure is obviously a key thing in these kinds of analyses in practice. The other thing that Nagar found was that when she used different numerical models, the input parameters that created a decent simulation of these historical cases were different for every model that she used, and they were also not exactly comparable with measured material properties that could be evaluated independently. So a huge challenge for numerical modelers is trying to estimate the value of the input parameters that you put into the models. And we were finding that it depends on the model that you use, and that you can't just go and measure the material properties and put those values directly into the model, that there's some kind of adjustment that might be needed. And then while all that other research was going on at Waterloo and UBC, students in the lab at Queen's University were creating these scale model dams and breaching them and looking at the results. So what you're seeing here, I think it's sped up to like 5 times. But this is an overtopping experiment of just a simple sand dam in the flume at Queen's University. And this work was started by Andrea Walsh, who was a master's student at Queen's. And she was looking at the impact of tailings dam specific geometry on the outflow hydrographs that came out of the experiments. So tailings dams, a little bit different in terms of geometry compared to water retaining dams. They tend to have shallower upstream slopes especially. And we were curious, it's been kind of an open question in the industry, how does that affect the calculations we make for things like the peak discharge of flows that might be coming out of these breaches. And Andrea found that higher peak discharges occurred with steeper upstream slope angles. So in other words, the shallower upstream slopes of tailing specific storage facilities would probably result in relatively lower peak discharges. So that's important for the results of these inundation studies. Another student at Queen's University, Kaylee Barlow, was looking at applications of this model called XBeach. And XBeach is a unique model. It was originally developed to look at beach erosion and breaches of barrier islands off of coastlines. And we were curious if this model could simulate these kinds of dam breaches that we were looking at in the lab as well. So on the right there, you should be seeing an animation of a simulation of Kaylee's work using the model XBeach. And she was able to find the pretty good correspondence between the numerical model results and the physical model tests that were done in the Queen's flume. So this is just an example of trying to explore new models that our industry partners were interested in potentially using in their practice. And then the third graduate student member of the team at Queen's University, Megan McKellar, finished her PhD there last year, and she was looking at extending the lab experiments that Andrea started to look at different mechanisms that lead to overtopping failure of these dams. So what you're seeing in the video there is seepage-induced failure. I'll just play that one more time. You can see it's instrumented with pore pressure sensors. She's cut off the drainage at the toe of the dam to try to increase the saturation of the material in the dam and induce this landslide essentially, which lowers the crest of the dam and induces the overtopping, the catastrophic overtopping that you see at the end of the video. And so we were interested in these different mechanisms that lead to overtopping and how that might affect the peak outflow of the material that's coming through a breach. No one has quite understood it up to this point. And what Megan's experiments were showing is that the sort of the mechanisms leading up to overtopping, it might give a little more advanced warning for when these failures may occur, but the actual peak discharge that we're measuring in the experiments wasn't really that different depending on the mechanism that induced overtopping. It was the overtopping phase that dominated, and once that started, it was fairly similar in all of the failure mechanism cases that were investigated. So I am going to go fairly quickly through that kind of summarizes the key work to date. And like I mentioned, we're kind of in this intermediate phase. We're bringing new students on right now to get started on the second phase of the research, trying to explore some of questions that have been raised along the way so far, and we've learned a lot. But and I think the practice has improved through these interactions with our industry partners and sharing some of the outcomes of our research. But a lot of questions have also been raised as we've gone, and there's a lot of interest in trying to experiment with real tailings or tailings-like materials now. We recognized through some of Nagar's work that I mentioned the sort of missing link between the numerical model inputs and the material tests that we can carry out. So we're trying to reconcile that. And then we want to pick up where we left off in investigating field behavior and looking at natural analogs that we might be able to use to understand more about these human-caused mass movements. So things are ramping up again in the flume at Queen's University. Students are back in the lab trying to prepare the flume for some new experiments. And the new experiments are going to include tailings-like materials, trying to extend the relationships for the erodibility of water-retaining dam materials that we understand fairly well, trying to extend that to tailings materials that we don't understand very well yet. We're trying to develop new relationships between storage volume and specifically release volume related to that material erodibility. And we're also running new experiments to provide new data to validate numerical models as we go. And one of the first things that the students are going to do is try to look at the influence of the position of the dam within the flume here. That kind of controls the storage of material upstream of the dam, and we're interested in seeing what happens if we increase or decrease the storage volume, how that affects the breach outflow.
Hello, Scott. It's just me. I'm just giving you a quick 5-minute warning before we'll try and go for questions.
Perfect. Yeah, the other thing, in the first phase of research, we were trying to do liquefaction experiments in the flume and found that in the stresses, the relatively low stresses that we could get in the flume, that we were really struggling to liquefy material. And so we're going to be running enhanced gravity dam break experiments in the new centrifuge facility that's being built at Queen's University right now. So you can see I got this photo from Andy Take a few days ago of the construction in progress. They're doing well, and we're hoping to bring in a new student to look at these kinds of experiments next year. One of the things that we're really interested in is the effect of partially saturated material on the failure liquefaction potential of tailings, but also on the mobility in the event of a failure. And that's a huge question for our industry partners, because not all material that we're dealing with is saturated. Also here at UBC, there's a new PhD student, Bruno Rodriguez, who's started recently, and one of his first tasks is to try to dig into this discrepancy that we see between the properties of the material that we can measure and the numerical model input parameters that we use for simulations. And so he's been compiling a huge inventory of measured material properties. So that's what you see in the chart here on the left, just the variation in viscosity measurements for different types of tailings. And they range over several orders of magnitude. And the same thing can be seen in the numerical model results. When we back analyze cases and try to calibrate the input parameters, we see variability over 1 or even 2 orders of magnitude. So Bruno is trying to dig into that and understand the underlying reasons, and then in turn try to give guidance to practitioners on how to choose appropriate input parameters for their numerical models. And then I mentioned waste rock storage at the very beginning of the talk. We're hoping to extend the research to look at the sort of relatively drier and coarser end of the mine waste spectrum. We do have technologies to dewater tailings and create stacks of relatively dry tailings, but they also fail. And the photo on the left is showing another recent failure in Brazil of a so-called dry stack. And then the waste rock piles also, are susceptible to failure, and sort of a classic example of a waste rock pile failure shown on the right there in the 1960s is this failure in Wales. that flowed into a town and unfortunately impacted a school. And so we're collecting data on these sort of unconventional tailing storage facilities and waste rock failure case histories and trying to run them through some more modern ways of looking for correlations. This is an example showing just simple multiple linear regression, looking at historical data that was collected up until the early 1990s on coal mine waste failures in Western Canada. And I'm actually traveling to some mines in eastern British Columbia tomorrow to try to seal the deal on a new data sharing agreement to get our hands on data that's been collected over the last 30 years or so to try to analyze that and add to this understanding. And then I mentioned, our kind of underlying goal is to create this community of practice around this topic. And so, I'm really proud of all the students that have gone through the project so far. We've trained about 18 students so far and counting. Many of them are working at the top companies now, including many of the original sponsors of this research. And one of the fun things as we go into this new phase is seeing the previous graduate students coming back to try to mentor the newer grad students as they go through. So all these former students are actually still involved in the project in some form. And yeah, I would just thanks again to Joshua for inviting me to share this ongoing work with you guys. And if there are any comments or questions, happy to try to answer them.
Absolutely fantastic. Thank you much. Thank you so much, Scott. I'm gonna stop the recording now so that we can go into some questions.